Hello, today we're going to be doing another titration, but a variation on it specifically for Unit 8. We're going to be looking at titration curves, so tracking the pH throughout the entire titration. The one that we're going to do in particular is an unknown ammonia solution. It's really ammonium hydroxide, but ammonia, reacting with a known solution of hydrochloric acid. And then have our full equation and our net ionic equation here. But what I will usually do when we're doing the titration curves lab is I will give each lab group a different titration to work on. So some of the options I'll do like an unknown hydrochloric with a known sodium hydroxide, an unknown sodium hydroxide with a known hydrochloric, an unknown acetic acid with a known sodium hydroxide, and the unknown ammonia with a known hydrochloric acid. Some other ones that I've done in the past, especially if you want to look at like the difference with diprotic or triprotic acids, or if you want a dibasic, but like sulfuric acid, phosphoric, this is citric acid, calcium hydroxide, if you have access to that, is an interesting dibasic one as well. So these are some different options, and once the students have obtained their titration curve, I have them kind of display it at the end of their lab station, and then we do kind of a gallery walk where the kids go and visit and see the different titration curves that were made. This saves a little bit of time instead of having each group do 4 different titrations. Each group does one and then sees the difference. This goes along really well if you are also doing some kind of particulate diagram representation throughout the titration itself. So I sometimes will have each group then create a large version of the titration curve that they created from their data and label like the particles that are present at each of the major points during the titration, and that way when the groups visit, then they can see like, oh, okay, these are the important bits that they need for that particular type of titration. Okay, so for this titration, I have our unknown ammonia solution in the beaker. We're using a beaker today instead of the Erlenmeyer flask. Typically, you'd want to use an Erlenmeyer flask so there's less chance of a splash. But in order to get the pH meter and the burette both have access to the rim of the solution there, I use a beaker for this. And then you can use just a normal stir bar, or if possible, there is a little stir attachment for the pH sensors, which is really nice because it helps to protect your pH meter. The only problem with this is that you have to use more of the analyte because it has to, completely cover the bottom of the pH probe. So then we want to set this up in the solution like this.
So it's mutual. I have actually a good
There we go. And we'll turn the stirrer on low. There we go. Okay, and so then we're going to titrate. Now, you can use an attachment like a drop counter. I have some of those. They look like this. You have to calibrate it to the correct size of the drop, and then it will essentially run the titration for you. I prefer to have students do it by hand, so that way they're connecting the volume of the solution and the pH to the pH curve, and it's a little bit more conceptually, like, it makes more sense to them that way. So what we're going to do is add about a half of a milliliter at a time, stop, record the pH and the volume at that point, and then add another half of a milliliter, do the same thing until they get a full titration curve. I've also included an indicator. I'm using methyl red. The indicator is completely optional. I like to use it just so that they can see where the endpoint is, but it is not really necessary for this lab. So here is the titration curve that we got for the unknown ammonia solution with a known hydrochloric acid. And it is by no means perfect, all right? This was taking a sample every half of a milliliter, all right? One thing that you can do is have students do like a quick titration, do like a every milliliter one and get a rough one so that they know roughly where the equivalence point is. And then when they get really close to the equivalence point, they can narrow their measurements down. So they can do it like every half or even quarter of a milliliter and record it that way. Of course, you're going to get a much smoother curve and more accurate curve if you're using a drop counter in addition to the pH probe. But again, I like to have students do it by hand. That way they can really get an idea of what's going on. So this is what we're seeing here. I have them estimate the equivalence point, which is roughly 9 milliliters in this case. It might be somewhere between 9 and 9.5 to get really that kind of halfway point. But I'm going to say 9 just for the purposes of this. So the half equivalence point then is important for our weak acids and weak bases. So we're looking for maybe the 4.5 realm in here. That's going to give us information about the pKa. So the pH at this point is equal to the pKa for the conjugate acid. So the NH4 pKa that we measured here was 9.48. Well, if we subtract that from 14, we can get the pKb of the conjugate base, which is 4.52. And that's actually not that far off. The pKb for ammonia is 4.75 at 25 degrees Celsius. So getting 4.52 is pretty close. But having them find the equivalence point and then half equivalence point, labeling that for each group as they move around. Obviously, if you're doing a strong acid, strong base titration, you wouldn't need to label the half equivalence point, just the equivalence point. So this is the information you really want students to get out of the Titration Curves lab. They need to be able to distinguish between strong titrations and weak titrations. They won't ever be titrating a weak acid or base with another weak acid or base for AP chemistry. But they need to be able to distinguish between those two. They should also know that the pH at equivalence point, when they're both strong, should be 7. Of course, experimentally it might be slightly off. But the really important point is at 7, and then the volume at that equivalence point will help us figure out the concentration of the unknown. Then for our weak titration curves, they need to know where the buffer region is for both of them. They need to know that equivalence point, the volume at equivalence point is still used to find our concentration, but the pH at equivalence point will be different. If you have a weak acid with a strong base titration, the pH at equivalence point will be above 7. Weak base with a strong acid, the pH at equivalence point will be below 7. They should also know, of course, at half equivalence point that the pH is equal to the pKa, which if you're doing a weak base, it's the pKa of the conjugate acid. So since we did ammonia in this lab, the pKa that we found was for the ammonium, which is important to notice. They should also have an idea of the ion concentrations at half equivalence point, before half equivalence point, and after half equivalence point. Of course, at half equivalence point, the weak acid has the same concentration as its conjugate base. Before that point, you have more acid, and past that point, you have more conjugate base. For this titration, again, you're going to have the base and the conjugate acid. It will be the same concentration at half equivalence point. Before that, you have more base, and past that, you have more conjugate acid. So these are the things you want them to kind of get out of while they're working. I will give them some hints before I let the students, rotate around and see, like, oh, hey, you're missing, the concentrations before half equivalence point. I'm like, oh yeah, and I'll add that in. So that's kind of everything that they need to know. In terms of errors for this, sometimes they'll talk about there's extra water left over in the burette. That's a really common one. So that means that the extra water in the burette, there's lower concentration than expected of your titrant. So your volume to reach equivalence point will be higher than it should have been because it's diluted, so you need more of it to fully neutralize the analyte. What's another common one? Just the fact that if you're using a indicator, the fact of using an indicator will introduce error if you're using the indicator to determine the equivalence point. So that it takes a little bit of extra titrant to react with the indicator and change its color, so that it will always be slightly past the equivalence point. Also, indicators don't necessarily turn color like right where you want it to, so depending on your choice of indicator. Now you could use calculus here to find the equivalence point, especially for those weak acid, weak base titrations. But it's a little bit past the scope of an AP chemistry class. I just have them estimate, hey, where's your most vertical point-ish? And it's usually pretty close. Well, for the strong acid, strong base titrations, I try to get them as close to 7 as possible, because they should know that that's where the equivalence point is for those ones. Yeah, so I think that's everything that they need to know about the Titration Curves lab. Really, if you can get them to do one of these, it's really useful because it gets them a lot of information that they need to know for the AP exam, all in one lab. There are some really good simulations online if you can't do the physical lab. There is also a really great website that will generate titration curve data for you. So again, if you're strapped for time or if you don't have the technology to be making your own titration curves, the simulation is great, and it is absolutely free, so you can generate this titration curve data and have them graph it that way, and get the same kind of information from there.